We're waiting for the green square and the flow. Hello and welcome back to Calculus 1 section 5.2 part 2. So in the first part of this lecture, first of all we had to interrupt this because we had to go urgently and walk outside. Now we're back and working on the second part of the lecture. So definite integrals, we defined what a definite integral is in terms of the Riemann sum, and then we enjoyed these calculations to find the value for the integral the long way. And then at the end of the second example I said, or we can do this, which is the definite integral. Technically what we did is we found the antiderivative first, and then we computed that antiderivative from 1 to 6, and we obtained the same answer as above. So now the formula which I mentioned last time is the formula that we use to calculate the integral. So integral from a to b of some f of x dx is equal to the antiderivative f of x computed from a to b, which is f of b minus f of a. You are going to get sick of this formula. It's going to be everywhere used a lot. So, as I said, across the sciences. So now we can use above to calculate area under the curve. So I'm going to start with the rectangle. Say you are tutoring mathematics for $50 an hour, this middle school kid, right? And area of the rectangle 5 by 3 comes up, and you say, and we know what the area for the rectangle is, and the kid doesn't, and then you say just 5 times 3 is equal to 15, and the kid goes, why? Let's see. You draw the rectangle in the coordinates system, right? X, Y. You draw the rectangle, so 5 on x-axis and 3 on y-axis, which means it goes from 0 to 5 and then from 0 to 3, realizing that this function on top is f of x equals to 3, realizing that your a is 0 and b is 5. So as soon as those words y come out, you just say, well, clearly integral 0 to 5 of 3 dx is equal to 3x computed from 0 to 5, which is 15 minus 0 equal to 15. And you proved your point. So hereby I give you the license to forget all of the area formulas you learned. Because you can find area of any shape if you carefully use this method. Let's say kid did not have enough beating. So the next y is on a triangle which had 1, 2, 3, 4, 5, 6, 1, 2, 3, 4 this way. Right. So you get those, oh yeah, it's just 1/2 base times height, so 3 times 4 is 12, and it goes y. Let's see why. I have immediately integral, so area is going to be the integral of f of x dx from 0 to 6. So you see that this interval is always a to b, which is the interval on the x-axis. So a b interval actually should be brackets. So a b interval is on the x axis. So that's where the 0 to 6 come from. But now, what is my function over here? What should I do? So lost, right? It's a linear line. You can find the equation of the linear line. Right? Right. So what do? You say we have slope, which is rise over run, go up 4 over 6, and it's negative because it's falling to the right. So the slope is negative 2/3. And what else you know? You know that the y-intercept b is 4. So immediately y equals negative 2/3 x plus 4. There's your function. So 0 to 6 of negative 2/3 x plus 4, all of that in parentheses, times dx in the notation. This dx is going to be -1 per time you forget it. Fair? So technically you can score -2 for a problem that had 12 dx's to write.
Can you get a negative
Let's do it.
number?
Yes.
Like, can you get a negative?
Well, depends on the amount of plus c's and dx's you forget.
Can you?
What if you forget all of them?
Yeah, that might offset your 100 to let's say a -3. But then if you do 3 quizzes, that pushes it right back up to 0.
We're trying to go down.
Can you actually like put a negative in the grade?
Yeah.
Okay.
Yeah.
Physically
Keep talking, you'll see. So now I'm integrating x squared over 2. So I have negative 2/3 times x squared over 2 plus 4x from 0 to 6. Twos will cancel. I have negative 1/3 x squared plus 4x from 0 to 6. And we know what to do. Plug in 6 first and then plug in 0. So that's going to be negative 1/3 6 squared plus 4 times 6 minus just big 0 and 0, right? We don't have to worry about that. So 6 squared is 36 divided by 3 is negative 12 plus 24, and here is your 12. So we see that there's no reason, there's no need to remember the 1/2 base times height, because clearly this is working. We did not discuss the efficiency of it, but you know. But the next question is, what is happening with other functions? What is happening with x cubes and square root of x and e to the x? You can find area under all of them. So what is the area under, let's say, from 0 to ln 7 of e to the x dx? You can graph that to visualize, right? So that's 0, and that's ln 7 is a number. That's what you're looking for. Area under the curve for the function e to the x from 0 to ln 7. ln 7 is a number. What's the integral of e to the x? Very good. Computed from 0 to ln 7. So you have e to the ln 7 minus e to the 0. How much is e to the ln 7? Very good. Minus e to the 0 is? Perfect. And then 7 minus 1 is? That's it. I know, it's math. I was able to shade the area, so shaded area is 6. Let's see, let's do 2 more examples. Find something interesting, hopefully. How about area under square root of x cubed dx, no coughing, from 1. I know.
Doesn't change anything.
Does not change. Why? You want me to have double standards? Exactly.
That's part of the issue lesson. Don't want to make this happen. That's what the last one said.
And then she became pregnant.
After lots of months, yes. What are your plans? Yeah? What?
After fun.
Isn't that
You're not zooming your position until July 1st.
what?
That's the job.
Yeah.
His job.
I'm the critic. What?
So how should we rewrite this problem so we can integrate? What should I write? Yes.
X to the 2/3. X to 3 halves.
3 halves, yes. So the square root is a half on the exponent, and then you will just use the +1 rule, right? Because it's x to some number. Any problem that is x to a number is always exponent +1 divided by exponent +1. So you will have this x to the 5/3 divided by 5/3, and then plug in the values. Let's do that. I feel young. Hey, we can start finally. There, good. Well,
You missed the walk part.
yeah, feel protest.
Yeah. Again.
Oh, wait.
No, the leader that lies is that
What? I actually do that. I mean, that's a constant, right? Like, and what's the derivative of a constant? 0, so it doesn't matter. All those times that I made fun of you, I actually wasn't making fun of you.
You know, the more you get picked on, the more you love.
Yeah.
That's actually true. That's true.
I get picked on a lot. Might be considered a bullying love, you know.
Yeah.
Yeah.
It's tough love. It makes you stronger.
Yes.
You gotta
Like,
laugh
well,
it
now
out.
you're executive VP.
Like, look
And
what I did.
look
with
what I
Brian
did
over
for
the
you.
years. What I did for Brian
Looking
over
for
the
reaction,
last
you
2
give it to
years.
him every time.
He has grown tremendously.
What was he saying?
Like, even people like him now.
Like, how my face is tall at all. I'm so readable. I agree with that.
Ali's face is so readable. This is Ali's face. Yeah.
Saying every word has a different facial expression.
You remember that famous pre-calc class when I walked in and said, hey class, hey bro. Put you in the category.
Yeah. Small letters. You should see. Now my bio professor does that as well. Like,
You're a magnet.
always calls
Listen.
me.
So we are going to rewrite this problem as x to the 3 halves dx from 1 to 5. And then we are going to add 1. So x to the 5 halves over 5 halves. And then we don't have plus c, we have now calculation 1 to 5. So this becomes 2/5, 5 to the 5/2, minus 2/5, 1 to the, I could have chosen a better number, but such is life. And so the 1 to the 5/2 is 1, so that's easy. The front, 2/5, and then you can take the, you can do the calculator to figure out, right, what is 5 to the, if you want the decimal, no one cares. That's exact. And you can figure out decimals if you want to. Great. How about sine? I know you like that one. Sine x dx from 0 to 2 pi. I know how much you love trig. I don't want to miss that. Very good question. Why don't we need plus c when we do these definite integrals? If I integrate, let's say, x dx from, let's say, 3 to 5, I will get x squared over 2 plus c from 3 to 5. And then I will have 5 squared over 2 plus c minus 3 squared over 2 plus c. When I distribute the negative, and that happens every time, so we never write plus c.
So is plus c
Indefinite integral, the one that will not have, so your 4, 9, and you will see the 5, 3 will clarify some of that stuff. So next section. So we just have to do one, maybe one more example, depending on how this one. So what's the answer? What's the answer? You have the limits, right?
Yeah, I was gonna say, like, consider it.
Close enough. All right, so this is the problem which leads us into the next section. If you do calculation carefully, you will get 0, and that will make sense in one frame of reference and not make sense in another. So the question here is, what do I want? Do I want to compute the value of the definite integral, or do I want to compute the area under the curve? And this example shows that they are not always 100% the same. So look what happens, guys. Sine x on 0 to 2 pi dips below x-axis for the negative area. So whatever positive area you accumulate up to pi will be exactly cancelled by the area after the pi for the net of 0. But you can't claim that the area is 0 because you can shade, right? You can shade, so area is not 0. You are, see, I'm using paint now. So I'm covering. So when you see problems, you have to make clear what is the question. Is the question area or just the value of the integral? Because if the question is area, you have to be clever to break the problem into two parts and deal with the second part using absolute value so that you are not subtracting and canceling stuff. So if I want the area, I have to go 0 to pi sine x dx plus the absolute value pi to 2 pi sine x dx to compute this. Now we all know that the integral of sine x is negative cosine x from 0 to pi plus absolute value negative cosine x from pi to 2 pi. So now when you plug in pi, negative cosine, so you get negative of negative 1 minus and then you have negative 1. I'm going to put another set of parentheses there. There we go. I'll explain all of these. Plus absolute value of negative cosine of 2 pi is...
Oh, no, it isn't.
All right. Minus another one. Now I have these weird looking parentheses that we might not want to, but let's take a look why I have them. So this minus is this minus, and then cosine of pi is negative 1. Are we all bueno on that one? Now this minus is from the formula because it's f of b minus, right? F of a. And then this first minus is this minus here. And the cosine of 0 is 1. So now when you look at the whole thing, it's just 1 plus 1, which is 2. Plus absolute value of negative 2 is equal to 2 plus 2 is 4. Which when I saw for the first time as a student, I was just blown away. Because we know how sines and cosines, they have all these root 2s and root 3s and pi's, and you never see a round number, right, anywhere. And all of a sudden, area under the curve, 4. Whoa, nice. Right? Nothing matches that.
That doesn't make sense.
So you just have to be a little bit careful with all of these excessive amount of negative signs. And you can't avoid it. So it's very easy to make a mistake. So don't make a mistake. So now we have this notion of area versus value of the integral. What happened with the e? Value of the integral. Same if f of x is above 0. Different if at least a part of f of x is below x-axis. And you've seen it with sine. And sine is a symmetric, right, function over there. So it cancels exactly. But it's very dangerous because some functions might dip asymmetrically. Say, you have a situation like this. You see? So if you have a situation like this is some kind of x cubed graph. See, x cubed has a, b, and c. Value of the integral is just integral a to c of whatever f of x is, dx, and you're done. But area has to go a to b of your function plus the absolute value of, not a to b, yeah, a to b and then b to c. So there is a difference between the value of the integral and area if the function dips below x-axis for whatever amount of space. A lot of mistakes happen here. Now these integrals, guys, they can compute velocities and position functions. They can calculate accumulation of energy. You don't solve differential equations and these integrals, well, you get the batteries that overcharge and explode. Sony had that issue. Like older batteries that were, in charges that did not cut off the power of the battery charge. So you're trying to push all this energy into device that can't hold it. Yeah. So these things are actually used. This is not something that you learn in school so you can pass, and this is, you're calculating these things in a set. Now also, across the field, we're talking sciences, we're also talking, accumulation of money, accumulation of everything that accumulates, rain, right? I think is it one of your problems on rain? I'm not sure which one, I forgot which one I put. What's the last one? Rainfall? Accumulation of rain, that's this. Right? So, there is a lot of stuff, guys, that can be computed with this. It's extremely, extremely important. All right, now we're going to switch to 5.3 and talk about fundamental theorem of calculus. Go on, just quickly restart the stream and change the title. We'll be back in a second.